Hello there! For today I prepared another screencast to talk about hidden line removal algorithm in OpenCascade, which is one of the fundamental functions of the library. So, why would we care what is the function, what is the purpose of this hidden line removal algorithm? Normally it's used in the situations where you want to project your part to get an outline of it, and those outlines are normally put into the PDF drawing so that you can compose a technical drawing and hand it over to manufacturer. So basically this is the functionality what you expect to find in any geometric kernel, and it's also the functionality of OpenCascade. For this lesson we have this little solution here as usual. So it's a simple main function with the viewer. We expect that as an argument to this solution the user passes the file name of the brep file to read. So in the debugging section here you're supposed to pass the command argument. And as it is always the case with our lessons, there is another solution in the repository, and in this solution you will find this data folder where I put for you a couple of files for testing. So for example, this ANC 101 is a standard part that was, by the way, designed using OpenCascade library. So I can take out its path and use it as an argument for our solution. Pass it here for the debug mode, and also pass it for the release mode. And again, so here we are going to read the geometry. For that we are going to use this brep tools read, and we have to pass here the output argument for the shape, then the path to our brep file, and then a brep builder that is just something that OpenCascade expects us to pass there for a pretty unclear reason, to be honest. It's not a step file whatsoever, it's just a brep file. If you wanted to pass here a step file or an IGES file, then you'll have to use a different tool. But let's give it a first run to see how it's going to work. Alrighty, so let's run it. And this is what we see on the screen. So it's just our part, ANC 101, in shaded view, and basically we want to project it to the outline and get something that would be readily available for composing up a technical drawing. So let's close it for now. Let's see how to get started with a hidden line removal algorithm, and for that, just in order to keep the code clean, I would prefer to create a separate function here. So let's imagine that we have a function named HLR for hidden line removal, and this function returns topody shape, which would be the projection of our shape, and it would accept also the input shape to process and the direction of projection. To pass the direction I can use with GPDir. So to remind you, GPDir stands for geometric primitive. Dir is the vector that is inherently normalized. So if I pass here some non-normalized coordinates like 1, 1, 1, then it will get automatically divided by its modulus. So be aware of this, and never pass here a vector whose magnitude is 0. So this would be the direction of projection. Now, coming closer to the subject, speaking about HLR, it's always important to distinguish between precise HLR and discrete HLR. Precise HLR is the algorithm that would keep in the projection result all those lines and arcs as analytical geometries, while a discrete HLR is a faster alternative that would give you the polygonized representation of the projection. If you want to read more about this subject, and especially about how OpenCascade's HLR compares to the same sort of algorithm in different geometric kernels, I would recommend you to read this little blog post with the comparative study. So this is a document where we compare OpenCascade's hidden line removal algorithm with some well-known tools such as SolidWorks, for example, or Rhinoceros, etc. So here you can find some comparative study. Basically, the main purpose of this study was to understand if the performance of OpenCascade projection algorithm is good enough, if we can reliably use it in commercial software. And I can say that the things are not that bad, so this algorithm definitely works, and we can use it with some tricks that we should probably discuss separately. Now, if you want to start with the precise HLR, then the algorithm to use is HLR brep algo. This is the class manipulated by handle, so you have to allocate it like this. And after that, you add a shape to be projected using the add function like this. So if you head over to the documentation of this class, you'll see, okay, this is the framework to compute a shape as seen in the projection plane. And then there is another algorithm that can be used for the polygonized projection, which is polyalgo, but we'll come back to it a bit later. So now, once we have this algorithm initialized, we have also to make use of this direction, which is the direction of projection. And to do that, to define the projection plane, we go like this. So we define the x coordinate system, x2 coordinate system, which is located in this case in the origin point of our world coordinate system, and then we define its normal vector to be the direction of projection. And then the HLR algorithm requires that we will wrap this plane definition essentially with the projector class. So this is how we are supposed to do that. Then to pass this projection plane definition to the HLR algorithm, you have to do something like this. You have to call its projector function, essentially to set this projector into the tool, and then to call a couple of methods more. Just write it down somewhere, and next time you copy and paste it to your code. And you see that, okay, we have this algorithm initialized, also initialized here. We have the projection plane definition, and now we have to take out the results of projection. To do that, we have to use this class, a separate extractor tool. Let me call it like extractor. This tool is initialized from the HLR algorithm, so it knows how to get the results out of the algorithm. And in this tool, if I look at the methods it offers, you see that I have quite some functions to call, and basically here is where I decide which types of the entities I want to take to my final view. I can take all the hidden elements as well, like all the methods containing this H letter mean that the hidden edges will be essentially returned. V stands for visible, so in most of the situations I would want to return only the visible elements of my projection. So why not to get started with this outline V compound function and see how it would work. And because this function returns Topodia shape, I can just go and return it right away. So now we have this initial version of the function to call, and I'll come back to my main function here and basically just call this HLR, pass in there my shape and also the direction of projection. That can be, I don't know, just some direction, 1, 1, 1. Those coordinates will get normalized once the direction is constructed. Now let's take this result as Topodia shape projection and display it using our visual stream projection here. Now I'm going to run it, so I'm doing it in debug mode, not sure how performant it's going to be, but you see it's already doing something, and the result is quite disappointing. What actually happened here is that I used a pretty arbitrary compound from the extractor, which corresponded to some outline edges or whatever, but I did not take care to read any sort of documentation, and I just took something out of it. So basically, I'm going now to share a piece of code with you, and I would highly recommend that you just copy and paste it to your application, because I mean, with the naming of those methods, there is always some question. So it's not particularly clear, at least to me personally, what these all methods mean. But this is something that I took from the OpenCascade sources. So basically there are two groups of shapes that we can extract, starting from V for visible shapes and starting from H for invisible shapes. Then there are some comments in some sort of like French plus English. And the idea now is, okay, first of all, we have this extractor that returns some compound. And the thing is that those edges that are returned by this extractor, they are all defined in the 2D space of the projection plane. So basically, those are just parametric curves that do not have any 3D representation. And you can easily check it if you dump those compounds to brep file, for example, then open them up in some application like Draw and then check what is inside. And you'll see that you have only two-dimensional curves, but you do not have any three-dimensional curves. And to fix that, if I want to have three-dimensional curves, we can put together this little function, build 3D curves. I define it right here. The idea behind this function is pretty simple. It iterates over all the edges stored in the past shape, assuming that this shape is a compound. We run an explorer, we iterate over all the edges inside our compound, and then we call a function of OpenCascade from breplib package, which is a static function to build curve 3D out of the parametric curve of an edge. It's possible to evaluate a 3D curve out of the parametric curve without specifying any surface explicitly, because the surface is already there. A parametric curve of an edge stores a pointer to the host surface. So we just have to reconstruct a 3D curve knowing the parametric equation of the surface. And this is what is done here. We iterate over all the edges, we rebuild all the 3D curves, and then we return this shape back. Because HLR does not do that for us. HLR returns all its results defined in this projection plane. So the results of HLR are essentially two-dimensional. Once we have all those compounds, normally we want to compose a scene, we want to compose the projection view, and for that I'm going to declare a compound like result, and then I'll just use some elements, some shapes from here to build the scene that I want. So let's call it like, first of all I have to construct the compound, of course, and then why not to add to this compound all the what is called like hard edges, or you may want to call them feature edges of your model. Then I also want to see all the smooth edges in my projection view, and I can now return this result and see what's going to change in the view. And you see that now I have like a perfect projection with a good property. If I select any edge here, you see that it's a real analytical shape. It's not a polyline whatsoever, because if it was a polyline, then I would have selected only like a small segment of this polyline. But here I have like a circular arc, and this is the good property of the projection of the precise HLR algorithm, because those analytical primitives can then be nicely exported to a format like DXF for a drawing, and in the drawing, if you check the entity, you will see, okay, it's a circle. Probably I have to add something else to the compound to have those edges also reported. Let's see like what will happen if I also add the contour edges. So I'll let you play with the components that you might want to add to this compound. Okay, contour edges did not help much. Maybe VO would do the trick. So this is always something that you have to play with. Now you see that I have I do not have my seam edges anymore over this cylindrical surface that has been projected, but I do have this, silhouette curves reported in the projection result. Now let's look at the alternative solution to HLR projection, which is a discrete HLR, and for that I'm going to create another function and call it DHLR for discrete hidden line removal. The implementation of this function is pretty similar to what we have done before, and I'll just copy and paste the complete code here and comment a bit on it. So again, we have to define the plane, the projection plane that would define the projection view. Then the same projector class as before is used to initialize our HLR algorithm with the projection plane. Now we have to use a different algorithm. Previously it was algo, now it's polyalgo. So this is a polygonal version of the hidden line removal algorithm. It's initialized in the same way. So we have a projector, load and update. And after that we have to use a different tool to extract the projection result. This time it's poly HLR to shape. So this is another type of an extractor to use. And this extractor is initialized with the polyalgo with our HLR algorithm. And after that, again, using the same more or less naming conventions, we extract the shapes that we want to put into the projection view. And we return the result. So this function is available now, and I can try to call it like here. So if I run it like this, I will run it using the debugger attached. Everything is being loaded, and now it crashes, saying that there is some null pointer somewhere. If I go to the call stack, then I will see that basically I am trying to add a null shape to my resulting compound. So you see that this T-shape pointer is just null. It's a clear indication that the projection has not been built, and why it happens here is because basically this polygonal hidden line removal algorithm expects the input shape to be meshed beforehand. So we need to have the triangulation constructed before we call this algorithm, because it's a discrete algorithm that projects not the shape itself, it projects its triangulation. And to prepare my shape for discrete projection, I can just go and call this brep mesh incremental mesh, which is a faceter of OpenCascade. Here I pass the shape that I want to be meshed, and also the deflection value, which actually has to be computed from the bounding box of the shape, but here I do not really care, and I use just some number. I only have to include this. After this invocation, my shape will get triangulated. Essentially, it means that in all the faces, all the cat faces of my shape, I'll have polytriangulation populated with triangles. And let's see if it's going to change anything. Yeah, you see now that I have another projection result, and if I select those edges here, you see that they are all discrete. So now, instead of nice analytical representation of geometry, I have just a polyline. But the good property of this polyalgo is that it's pretty fast, so it usually takes like a fraction of a second, and you do not have to wait indefinitely long for this algorithm to converge and to give you some projection view. That's probably all what I wanted to cover in the scope of this little screencast, because we can talk for hours about this HLR and different tips and tricks around it. But I would rather recommend you to head over to the corresponding blog post, where we compare precise HLR and discrete HLR, and here we discuss some of the interesting techniques, how we can limit the execution time of the algorithm using OpenCascade threads, which is another topic in itself, but it will be too heavy to try to cover it in the scope of the video lesson. So I hope you will find it useful. If you have any questions about HLR and how to employ it, you can also check the source code of the lesson in the repository. It's lesson number 23, and by the way, if you look inside this main function, you'll see that it's way more advanced than what we just covered, because here it uses threads and some supplementary data structure to define the projection result. So basically, I do not want to stay here to explain all this, because it is all written here in this blog post, but still it's some good start for you guys if you want to integrate something like hidden line removal into your application. If something remains unclear, go ahead and join our forum where we can discuss all these things. Thank you for watching and see you next time.